Finally, we are close to the end of the proof of the prime number theorem. Based on our previous reduction and new notations, now it suffices to show that alpha is equal to 0. I copied the definitions for alpha and beta as well as two lemmas we just proved concerning the integrals of the function v. And at this point, you may not remember the definition for v, but I will recall this definition when we use it. So don't worry. You might want to pause here and take a screenshot. But I will move on. As I mentioned from the beginning, our proof will be by contradiction. Now we assume alpha is bigger than 0. Then we will show the following. We will show for some choice of delta bigger than alpha and alpha prime less than alpha, we have the following estimate of the integral from zeta to zeta plus delta of the absolute value of the function v with variable eta d eta less than or equal to alpha prime times delta plus little of 1 as zeta goes to infinity. And we will use this to conclude that the integral from 0 to psi of the absolute value of v of eta d eta is less than or equal to alpha prime times psi plus little o of psi. And from here, we will conclude that beta, which is defined as lim sup of the average as psi goes to infinity, is less than or equal to alpha prime, which is less than alpha. So this is our basic plan in this final section. And of course, the tricky part is how to pick this delta and alpha prime. And now, let me give away one spoiler. I will tell you what this delta we're going to choose. We will eventually choose delta as the following quantity: 3 alpha squared plus 4a1 divided by 2 alpha. And you can easily see that this number is bigger than alpha, where a1 is a positive constant, as in theorem 435, which is a uniform bound for all such integrals. This a1 is an absolute constant. But the reason for this choice will be only fully revealed in the end. From the beginning, you can just assume there is some delta bigger than alpha, ignoring its specific definition. Our first goal is to prove this inequality. And to this end, we need to understand this integral. So to understand the integral, we need to understand the behavior of the function v of eta on an interval. Now at this point, let me recall the definition for v of eta. By definition, v of eta is psi of e to the eta divided by e to the eta minus 1. And psi of e to the eta is defined as the summation of lambda of n's for n less than or equal to e to the eta. And recall, this lambda of n is equal to log of p if n is a non-trivial power of p. Otherwise, it is 0. Now let's see the monotonicity of the function v of eta. To this end, let us first study the monotonicity of the function psi. Psi of x is a monotonically increasing step function, and you might want to draw a graph of it. It is locally constant and monotonically increasing, with jumps whenever x hits a power of prime. Now, what about the monotonicity of the function v of eta? By looking at the expression of this function, you can easily see that as eta grows continuously, the denominator will grow continuously. But the numerator is a locally constant function with jumps whenever this e to the eta hits a power of prime. So to summarize, v of eta is monotonically decreasing, except for the points where psi of e to the eta makes jumps. And let me try to draw a very inaccurate picture, so that only gives an idea of this behavior. By no means this picture is an accurate figure. The graph of the function v of eta looks like this. For the most of the time, it is monotonically decreasing until e to the eta hits a point that is the power of prime. Then it will make a jump and starts decreasing again until e to the eta meets another power of prime. Make a jump and starts decreasing again, and so on. So this is the behavior of v of eta. Now, for any zeta greater than 0, over the interval from zeta to zeta plus delta minus alpha, there are only two cases for our function v of eta. Case 1 is that for this zeta bigger than 0, there exists a naught in the interval from zeta to zeta plus delta minus alpha. Note that it naught depends on zeta, such that v of it naught is 0. And here, let me make a remark that eta naught may not be the only 0, just some 0 of the function v. And this is the first case. The second case is the following. If, on the other hand, for this zeta bigger than 0, v of eta is non-zero for all eta in this interval, then v of eta changes sign at most once. This can be seen from the picture. Let me add some explanation. since v of eta can only jump up, not jump down. If v of eta crosses 0, continuously, then v of eta will be 0 for some eta in this interval. But then it will fall into the case number 1. So in the case number 2, this should not happen. And the only case where this v of eta can ever change its sign is when there is a jump up. This curve will not just peacefully, continuously cross 0 at some point eta in this interval. That will not happen. And if it jumps up twice, then by the mean value theorem, in the middle, there must be a point where this v of eta hits 0. I hope this explanation makes sense. If not, please let me know in the comments. I will try to explain again to you. Now we will estimate the integral of the absolute value of v of eta from zeta to zeta plus delta based on these two cases. For case number 1, namely v of eta naught equals 0 for some eta naught in the interval from zeta to zeta plus delta minus alpha, we shall split the integral into 3 parts. And let's analyze these 3 parts separately. First, for the part eta naught to a naught plus alpha, we can bound it by alpha squared divided by 2 plus big O of 1 over eta naught. This is precisely theorem 436. Theorem 436. Where we use that eta is the root of v. Now what about the first integral and the third integral? To estimate these two integrals, we first recall by the inequality 22.15.10, which says that the absolute value of v of eta is bounded by alpha times little of 1, which is the quantity that will go to 0 as the variable psi goes to infinity. So in our setting, by 22.15.10, v of eta is bounded by alpha plus little of 1. For the variable eta in the interval from zeta to eta naught, union the interval from eta naught plus alpha to zeta plus delta. Note that the lower bound for this union of two intervals is zeta, and eta lives in here. So this little of 1 will go to 0 as zeta goes to infinity. Now, applying this upper bound for the integrand in the first and the third integral yields And by cancellation, what is left from here is simply delta minus alpha. Now we add up these two upper bounds together. And let's simplify this. But as I stated at the beginning, the choice of delta will be bigger than alpha. So this part is really bounded by delta times theta of 1. And moreover, this delta is a fixed absolute constant. Alpha is actually an absolute constant. We already know alpha as a supremum of the absolute value of v of c is finite. This is a fixed absolute constant. And so is delta. Therefore, you can throw away this absolute constant. On the other hand, because this eta naught is bigger than zeta, so 1 over eta naught will be bounded by 1 over zeta. But the zeta is a sufficiently large number, which means this guy will also be a little of 1 as zeta goes to infinity. So we can combine these two further together. And from here, let me just do one more step. We'll pull out this delta outside. And later, we're going to define this guy as our alpha prime. But at this point, you don't have to memorize that this is alpha prime. You will see again this thing later. This finishes the estimate in the case number 1. Now let's turn to the case number 2. In this case, the function v of eta changes sign at the most once in that interval. If v of eta changes sign just once at the point eta equal to eta 1 in the interval from zeta to zeta plus delta minus alpha, which contains this eta 1. We have, by our lemma, the theorem 435, the uniform bound theorem, that the integral of this absolute value can be split into two parts. And now, because the function only changes sign once at this point, we can drop this absolute value sign here, because on these two intervals, this function is either always negative or always positive. So we can put the absolute value sign outside of the integral. And now we can safely apply theorem 435. By this theorem, uniform bound, these two are both bounded by a1, and together they are bounded by twice of a1. So this is the case when v of eta changes sign just once. Because v of eta changes sign at most once, so the other case must be v of eta does not change sign at all. That is actually an easier case. Then the same integral here will be equal to the integral where you move the absolute value sign outside, which by theorem 435 is bounded by a1. So in either case, the general bound for this integral is twice of a1. And we will use that bound next. Hence, the integral from zeta to zeta plus delta of the absolute value of v of eta d eta. Let's split this integral into two parts. One from zeta to zeta plus delta minus alpha, and the other from zeta plus delta minus alpha to zeta plus delta. The first part, based on two subcases in case 2, is always bounded by the more generous bound twice of a1. So this is less than or equal to twice of a1 plus over the second part. To bound the second part, we're going to use 22.15.10 again to bound the integrand by alpha plus little of 1. And by the same reasoning as we argued in case number 1, this little of 1 will still go to 0 as zeta go to infinity. So by 22.15.10, this is upper bounded by 2a1 plus this guy minus this is alpha times an upper bound for the integrand, which is upper bounded by alpha plus little of 1, where this quantity goes to 0 as zeta goes to infinity, because this eta is between these two numbers, and the delta minus alpha is positive. So this guy will go to 0 as zeta goes to infinity. And now let's do a small trick by pulling out a delta from here, as we have done at the end of the case number 1. Now we compare this with our result from case number 1. This was what we obtained from the case number 1. Now I'm ready to review the reason for our choice of this delta from the beginning. Why did we make this choice? That choice for delta was obtained by setting this guy equal to this guy, so that you get just one bound for this integral in either case. Solving this equation for delta yields delta equal to 2a1 divided by alpha plus 0.2 alpha. This is a number bigger than alpha, and this number is precisely our choice from the beginning. And we put alpha prime equal to alpha minus alpha squared divided by 2 delta, which is a number less than alpha. And this is exactly what is in these two parentheses. And we will use this later. It follows that in either case, this integral is bounded by delta times alpha prime plus little of 1. Where little of 1 goes to 0 as zeta goes to infinity. This verifies it, our first goal in this section. And now we'll try to conclude this guy. To estimate this integral using this bound, we're going to use the following trick. We're going to subdivide this domain of integration into small intervals of length equal to delta. How many such small intervals are there in the subdivision? Roughly, there will be capital M equal to psi divided by delta floor many. So we denote this integral by M. And this integral will be equal to plus the remainder term, the integral from M delta to psi of B of eta absolute value d eta. Now we apply this estimate to this integral for each M. And for the second part, we're just going to use the trivial bound for it. The trivial bound is that first, psi minus M times delta is less than or equal to delta. So this guy is always less than or equal to delta. And the integrand, this function v, is always a bounded number. So this integral will be bounded by a delta times big of 1. Which is again a big of 1. So because this guy is less than or equal to delta, and delta is an absolute constant, as we put here. So you can merge this guy into big of 1. So let me just erase it. And let's continue to see what this sum will give us. The sum is equal to alpha prime times delta times how many terms? M terms, plus little o of capital M plus big O of 1. This guy, because delta times M is always less than or equal to psi. So the first term is bounded by alpha prime psi. What about this thing? What is little of M? Note that this big M times delta is less than or equal to psi. So this is also little o of psi. As psi goes to infinity. But big of 1 as a bounded number is also little of psi. So you can merge these two together. And with this, we finish the proof of our second goal. And now we are ready to conclude a contradiction. You should feel excited at this point because this is the very end of the proof of the prime number theorem. Hence, our beta, which is defined as the lim sup of this average, now you divide both sides by psi. What do you see? You see this is bounded about by alpha prime. When you divide both sides by psi and let psi go to infinity, this little part divided by psi will go to 0. So this is less than or equal to alpha prime. But by our choice of alpha prime, that alpha prime is less than alpha. So we conclude that beta is less than alpha. But this is a contradiction to the result that alpha is less than or equal to beta in the previous section. And the source of this contradiction comes from the assumption that alpha is positive. Therefore, alpha cannot be positive. So alpha must be 0. And that is precisely what we need for the prime number theorem. So with this, we finally finish the proof of the prime number theorem. If you have watched this video series this far, I would like to say congratulations and thank you. Thank you for your patience. As we did with the Chebyshev theorem, let us state and prove a corollary of prime number theorem, which gives an estimate of how large the nth prime is in the increasing enumeration of primes. To prove this, we simply put x equal to p sub n in the prime number theorem. Then it follows that p sub n divided by log of p sub n is similar to pi of p sub n. But pi of p sub n, by definition, is precise n. So this is the precise number of primes less than or equal to p sub n, which is n. Then it follows that if you divide both sides by n, this ratio will go to 1 as n goes to infinity. Now we take the log of both sides. It follows that log of this quotient Pn divided by n times log of p sub n converts 0 as n goes to infinity. But if we break this down and we divide both sides by log of p sub n, it still goes to 0 and it simplifies to, and this guy will go to 0 as p sub n goes to infinity, because there are infinite many primes. So it follows that this part converges to 1, namely log of n divided by log of p sub n converges to 1. And therefore, it follows from that n is similar to p sub n divided by log of p sub n, that P sub n is similar to n times log of P sub n. And using this, we conclude that P sub n is similar to n times log of it. And we're done. So how large is the nth prime? It is roughly n times log of it.